Now, an important topic in this discussion will be measuring the polymer characteristics during the reaction. This is being done using a technique developed by us, ACOMP, which is a non-chromatographic method, although in certain applications we can enhance its performance by adding a SEC train. Principle of this method is very simple. It's based on a continuous extraction and dilution of a viscous reactor liquid, producing a stream through the detector so that the detector signals are dominated by the properties of single polymers and not by their interactions. A typical setup is shown below. Front end, which contains reactor, solvent, and the whole stages actually of where the dilution and conditioning is made. This includes multi stages of pumps and mixing chambers, and it represents the key of the successful monitoring. Once the solution is diluted, it goes through the detectors, which could be a light scattering detector, viscometer, refractive index detector, and UV detector. Optionally, one can add an injector, automatic injector, and GPC columns, and more detectors, and could have in the same time SEC monitoring of the reaction. Some complete ACOMP systems in our lab will be typical custom-built ACOMP. As you can see, reactor, front end, and detector train. Or you could have the commercialized version of ACOMP, where everything is nicely built and contained. It's user-friendly, software modernized and up-to-date. What do we study with ACOMP? Multiple applications from free radical homo and copolymerizations, step growth, controlled radical polymerization reactions, all done in batch, semi-batch, continuous reactors. We deal with solvent, bulk, or heterogeneous phase polymerization reactions. We go into predictive and feedback control of these reactions, post-polymerization reactions, and we monitor evolution of stimuli responsiveness in tailored polymers. Everybody knows kinetics of the polymerization reaction contain a few key features, and QSSA is one of the main one, and we are able to prove the main features by following our reactions with ACOMP. Typical ACOMP data is shown in the next figure. What is shown here are signals from detectors during a leaving copolymerization of butyracrylate with methyl methacrylate. So what we have is, first we start with solvent baseline to stabilize the detector. Then we add the first monomer, butyracrylate, and you can see Ri and UV response due to the difference in the dm by dc, respectively extinction coefficient. We add the second monomer, the signal responds as well. Then we add the catalyst, and as the temperature reaches the desired setup value, reaction starts. This is being seen by the drop in UV, indicating the monomer is consumed. In the same time, viscosity, refractive index, and scattering increase, indicating the polymer production. This raw data allows us to determine important polymer features, and one of them is concentration. From continuously collected Ri and UV signals, we can have comonomer concentrations, in this case styrene and dimethylaminoethyl acrylate, the two comonomers involved in this reaction. We can see in black it's styrene from ARA and UV, in blue it's DMIA, but also because DMIA is a charged monomer, using conductivity measurements, we can have its concentration computed. The discrete points represent measurements from samples taken from the reaction and measured by SEC. Monomer conversion. Once we have the concentrations, it's very easy to have monomer conversion, and shown here are free radical data from free radical polymerization of acrylamide and conversion curves for reactions done under different conditions with first order function fits as predicted by QSSA for free radical reactions. We can see the QSSA establishes faster for reactions done with higher initiator content. Slight deviations are seen for a low initiator concentration. Molecular weight is obtained by monitoring scattering and refractive index UV signals. Shown here are molecular weight curves for a few reactions during polymerization of the acrylamide, and these show also the nice behavior according to QSSA approximations and kinetics of the free radical reactions. Contrasting behavior is shown in the next graph in molecular weight in control radical polymerization versus free radical polymerization. One can see nice leaving behavior, linear with conversion for nitroxide mediated reaction, which is a leaving type, versus the behavior of molecular weight in a free radical polymerization reaction. High molecular weight at the beginning, smaller chains toward the end. The dots represent SEC measurements. Radical transfer reactions are commonly occurring and the radical could be transferred to a monomer, to another chain, to solvent or other molecule. Generally, the effect of chain transfer is to shorten the chains. We show here a few applications. First, chain transfer in free radical polymerization. An example is the effect of alcohols used as chain transfer agents on the polymer molecular weight in the case of free radical polymerization of acrylamide. One can see as the ethanol concentration increases, the molecular weight reaches smaller values as expected and predicted. The same behavior is shown by SEC. Here we have different, the curve on the right is a molecular weight distribution for polyacrylamide where no chain transfer was used. The next one shows the effect of ethanol, and the last curve is a molecular weight distribution where propanol was used as chain transfer, and you can see it's more effective. Chain transfer effect was studied also in emulsion polymerization, and it's a huge effect in this case. And an example is in the free radical polymerization of methyl methacrylate, where N-dodecyl mercaptan was used as a chain transfer. One can see the huge effect on both molecular weight, which decreases from millions to a couple of 100,000s, but also in the reduced viscosity, which goes down from 1,000 to in the tens regime of centimeter cube per gram, and shown On the right is the effect of the different concentrations of chain transfer agents on the reduced viscosity. One can see the same dramatic difference made by the addition of the dodecyl mercaptan. An unwanted chain transfer was observed during living polymerization, which was a nitroxide-mediated polymerization of butyl acrylate in butyl acetate. Here we can see deviations in molecular weight, which starts nicely controlled. And these deviations are occurring towards different stages in conversion depending on the transfer ratio used. Another type of transfer is in the raft polymerization. Here we have monitored the livingness of the controlled radical polymerization. Basically, we did follow the transition from living-like behavior in the controlled radical polymerization regime to the non-controlled radical polymerization regime. So shown on the right is molecular weight versus conversion for different reactions done with a different amount of raft catalyst. So where in the reactions where a lot of catalyst was used, of living behavior is accomplished, the less catalyst is used, the more deviation from the targeted mass is observed. And the last reaction here, the one on the top, it's a free radical one, typical behavior.